Hello and welcome to this session. So, what we will do in this session is to use the programs for matrix inversion and matrix diagonalization and illustrate how you can invert and diagonalize matrices. As far as the diagonalization process is concerned, we will only get the largest eigenvalue. Inversion we will do for any matrix, any size n by n. So, what you will see now, I am in my program directory. In my program directory, I have created many subdirectories to illustrate different tasks that I am going to do. So, let me do this ls. When I do ls, it gives me the list of all the programs and which are the directories. Can you see those directories with a light blue color? See, this light blue color will be one directory intrp. Okay. So, let me. So, what I have done here, I have listed all the files in my directory prog. So, these are all my directories and you will see that whichever are directories will come with a different color. So, that is the Linux operating system. I have a directory interp where I have discussed the programs for interpolation. I have a directory matrices in which I have put all the programs and all the executable programs like a.out, bexec, they are all written in a yellow color. So, let us see the same thing. I do ls minus l. Okay. So, when I do ls minus l, you will see that the directories come with this blue color interp matrices and the executable files will come in this yellow color. Okay. So, you will see this, in that you may see either yellow or a bright color, bright green color. Okay. So, now I want to go to my directory matrices in which all the programs are there. Let me list all of them. Okay. So, my programs there are matinvert.f, that is the program to invert matrices. Now, I use several versions of that mat inverse and the one which worked best, I have called it matinv-ok.f. This is my mat inversion program and the other program is eiglar.f. This is the program to get the largest eigenvalue of that matrix. Okay. And for all these I will need input. So, that I have called it input1.dat and whatever output is there, it will write as output.dat. Output will be the output of the program. So, now let me edit this matinv.f to find what that program is. How do I edit? vi. So, this is matinv-ok.f. So, this is my program. So, okay. So, some things you are not able to see. Okay. So, to do that, what I shall do, so now you are able to see the whole thing on your screen. So, I have inserted those extra lines here initially, I shall delete before compiling. Okay. So, we want to understand this particular program matinv.f. I had started it in one lecture before the last. This is an inversion program. So, I want to do it for a 4 by 4 case. First line is a comment card matrix inversion program by Gauss elimination. Okay. So, I need several matrices there. So, I have called it A 4, 4, B 4, 4, A old 4, 4, C 4, 4. This is my dimension statement and remember the dimension statement can also be written using real. Okay. So, I did not say dimension here, I just say real A 4, 4. So, this gives the array A, the A which is a variable, it will now a matrix 4 by 4 matrix. So, these are my arrays that I need in my program. So, now there is a parameter n, I can define parameters to this parameter statement. The advantage of that is you do not have to change n in the rest of the program. Suppose it is a 4 by 4 case. So, instead of writing 4 everywhere, if I just say n equal to 4, it takes n to be 4. Okay. See, there will be many read and write statements where n is used. So, if I use this parameter, I can write my entire program with n as a variable and suppose instead of 4 I want to do 5 by 5, I just take this n to be 5. So, this defining parameters in a program is a very effective way of programming. So, I have defined my dimension statement, I have defined my parameter, I open unit equal to 11, file equal to input1.dat, my input 1 has the input for this inversion program, the results I want to write it as output.dat. Okay. Then I need some small number, because remember we are going to divide by the diagonal element of that matrix. So, if that diagonal element is very, very small, I cannot divide by a small number. So, what is small? 0 is not necessarily the best way, because for computer it has only 8 digits after the decimal point for a single precision. So, a number which is 10 minus 8, I am going to take it as a very small number. So, I do not want to divide by any number smaller than 0.000000001. So, this is my small number. So, now I come to this write statement. Oh, this write 12 comma star does not do anything, it just writes a blank line. Okay. So, but see this, this was a comment card, see write 12, this is just a blank line, nothing is done. This write statement, write 12 comma star, the original matrix is. Okay. So, it tells me that on the screen it will write the original matrix is. Okay. So, the read statement is this, read 11 comma star aij, j going from 1 to n, I going from 1 to n. This is the statement where I read all the elements of that matrix. Two implicit do loops are there, j going from 1 to n, I going from 1 to n. So, I am going to read all the rows first, and first row is read first because I is 1, then j goes from 1 to 4, ai1, ai2, ai3, ai4, first row is read first, then second row, third row, fourth row. Then I also write that matrix in file 12. Remember, I have mentioned to you that whatever you read, you write it, so that you know what calculations are being done. Okay. So, then what I want to do, the original value of a, whatever original value of a was there, I will save it in a old, because the moment I change the values of a, remember in our operations by elementary operations, the values of a go on changing during the process. So, the original values I want to save in a variable called a old. Okay. So, these loops here now, what the next loop does, it writes all the values of aij into a old ij. It also, now the next the task is I want to define a matrix B, which is an identity matrix. Remember, whatever elementary operations I am going to use, I am going to operate with the elementary operation on matrix A as well as a unit matrix. So, my B is a unit matrix. How do I define a unit matrix? Look at this loop. I set all Bij equal to 0 except when I is equal to j. If I is equal to j, then Bij equal to 1. All the rest it is 0. Okay. So, this if statement I use it to make all Bij values 1 only when I is equal to j. Okay. So, that completes my definition of B as an identity matrix. So, what is my next task now? So, I want to now start dividing by the diagonal element. Okay. So, first elementary operation has started. I want to k going from 1 to n. Okay. So, my operation has started now. Okay. So, I will just see whether, so k equal to 1 means I am now going to divide by akk, the diagonal value of the first row. So, I check if I call akk as div, div is defined as akk, and if the absolute value of div is less than epsilon, remember epsilon I have already taken to be 10 minus 8, if this is less than that, then I do not want to divide, I want to exchange the ith row and the row corresponding to the largest value of elements in that first column. Okay. So, that is what I am going. I am going to, with these lines I am going to exchange the largest value in that particular column. Okay. That is what I am going in this particular loop. Okay. Where is my loop? Okay. K old is equal to k, highest equal to 0, absolute value. In that particular column, I find the largest value, whichever is the largest value, I exchange that particular row. See, I am exchanging that particular row with the first row. So, this is needed only when my diagonal element is 0. In our case, 0 means less than 10 minus 8. So, I have done this exchange procedure. Okay. So, now 282, this what does this 282 do? That k goes from this k goes from k plus 1 to n, because it is already the loop which is having an index k. So, the remaining lower values in that particular column I am exchanging with the largest value in that particular column. So, all this is just to exchange, this 282 loop is to exchange my present row with the row in which that particular column, in that particular column that value of the matrix is the matrix element is the largest. So, this exchanging I am doing here. Okay. So, then next, now I have to divide, I have to divide now. So, whatever exchanging I did for row A, I should do that exchanging for row B as well. Remember, A and B are identical. So, whatever I do on row A, I do exactly on row B. Okay. So, when I do this exchange, it is writing on the screen exchange rows k and k high, it exchanges those two rows and I write on the screen. Now, I start the division procedure. Okay. So, what is the, before that I have a determinant which I have initialized to 1. Whenever I exchange rows, the determinant changes sign. So, I am putting determinant is equal to determinant into minus 1. Okay. Now, my div is akk. Okay. So, I am going to divide now, and in case all the elements in that particular column are 0, if all the elements are 0, then one of the eigenvalues is 0. Okay. So, therefore, then I cannot calculate the inverse of a matrix. Whenever I cannot calculate the inverse, then I will print on the screen matrix is singular, therefore, I cannot calculate the inverse. Remember, whenever the determinant of the matrix is 0, okay, I cannot calculate the inverse. Okay. So, inversion is only for those matrices where the determinant is 0. So, whenever it is singular, go to 999, it is just, it will end the program. When you go to 999, it will end the program. If it is not 0, then I shall do these operations. I am going to divide akj, okay, all the elements of that column, kth column will be divided by div. Okay. So, naturally the diagonal value will be 1 and all the rest will be divided by div. Okay. So, this all the akj's will be divided by div and this completes the loop, and all the bkj's will also be divided by div. Okay. So, what does it do? It normalizes the diagonal value. Once I normalize the diagonal value, my next job is to replace each of the other rows by linear combination of the ith row and the pivot row. Pivot, let us say that the diagonal value was not 0, then I am going to exchange the remaining rows by taking combination of the new row and the old row exactly, so that all the remaining values are 0. So, remember what I am doing now, look at this loop. Okay. I am going to take the new aij will be old aij minus multiplier times the old value of akj. What is this multiplier? That particular value in the column. Look at our previous lecture which tells you how to set all the elements in that particular column to be 0. This is exactly that procedure to set all elements in the column other than the diagonal into 0. So, this is basically, remember we called it EI k of c. Remember this elementary operation was there, EI k of c, you multiply that so that all the non-diagonal elements become 0. So, this is, I do this for A, then I do this for B, that ends my loop. Then once I finish for one particular column, then I go to the next column. So, next column I repeat the same procedure, whatever I did for the first column, I will do for the second column, third column, fourth column. So, since this is a 4 by 4 case, I will repeat all those operations for the 4 columns. Okay. So, when I do all those operations, okay, whatever was my original matrix A, that has now become the inverse of A, and what A has become, A has become the identity matrix and B has become the inverse of A. So, to check that, what do I have to do? I have to multiply old matrix which was A old, okay, and I multiply that A by the matrix B. So, I take the product of original A and B, and the product of the original and the inverse should be identity matrix. Okay. So, these are the operations now. So, to summarize what I have done, I divided by the diagonal values to make the diagonal value 1, all the off diagonal elements I set to 0, and I did this for every column of my matrix A. So, the resultant would be A is now a unit matrix and B is a inverse of A. Then I also multiply A and A inverse to check whether it is an identity matrix. Okay. So, these are all the remaining programs. Now, I will compile this program. Before I compile these programs, initially I had some blank statements. So, what I shall do? I shall remove all the back statements. So, okay. Escape, then shift colon, okay. So, now, so I will compile this program by typing GFORTRAN, G Fortran, MATINV, matin-ok.f. When I compile that, so I have got a result like this. So, you will see that I compile the program by typing vi matin-ok.f. So, it compiled and it has given me a new a.out. I will execute this program. I will execute this program by typing /a.out. Okay. So, when I typed a.out, it gave this 1, 2, 3, 4. This output is just to indicate that I did my first column, second column, third column and fourth column. So, my results are now output.dat. You see this line output.dat. It has created a new output.dat. How do I know that it is new output.dat? This output.dat was created at 12:41. Now, let us do an ls minus l again. When I do ls minus l again, okay. See this ls minus l, just now I created a new output.dat by executing this a.out. Okay. Since I executed this a.out, I got a new, look at this, earlier one was 12:41. So, the new one is at 15:41. I have just executed at this time. Now, I want to edit that output.dat vi. So, when I edit that, okay, okay. So, what it did, it wrote the original matrix. On your screen you are not seeing all those things, but the original matrix is first element is 119, 2, 0, 0, 3, 0, 3, 8. The third line is 0, 7, 1, 4. You are seeing the third line here, and the fourth line is 0, 8, 2 and 9. So, this is my original matrix, and the first AKK was 119, okay, and it tells you whether it exchanges rows or not. Okay. Whenever it exchanges rows, it will tell you it has exchanged rows k and k high. Okay. Second time AKK was 8, there was no need to exchange. Third time AKK is 1, fourth time AKK is 8. So, these are my 4 operations. My determinant now is the product of all the diagonal elements. What are my diagonal elements? First value is 119, second one is 8, third one is 1, fourth one is 8. Okay. So, this is my determinant is the product of these values. Okay. Then what are the elements of the inverse? It is writing now these are all the elements of the inverse which are obtained by taking the matrix B and repeatedly converting it into the inverse matrix. Then to make sure that the inverse is actually the inverse, what I will do, I multiply this inverse matrix by the original matrix. Remember, the original matrix was A old. So, the product of inverse and the original is written here. See, this is the last particular 4 by 4 matrix 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So, this is a identity matrix I obtained in two different ways. One by taking the inverse and multiply by the original matrix. Second way by converting matrix A into the identity matrix by changing the columns and rows by the elementary operations that we have described in detail. So, before I go further, let us just edit that input dot dat so that you know what it is. So, Vi okay, I am not seeing anything. So, it is called input 1 dot dat. So, I will do, let me show here. You see here, these are all my files in my matrices subdirectory. The file is called input 1 dot dat. So, when I say Vi input dot dat, it gave me nothing, okay, because there was no file input dot dat, it gave me a blank file. So, I came out and now I will edit Vi. Okay. So, this is my matrix. So, since my screen and your screen are different, okay. So, this is my matrix. What was my matrix? 119, 2, 0, 0, 3, 0, 3, 0, 8. This was my original matrix, okay, and I used it to do all the calculations. Okay. So, since we have now found how to find the inverse of a matrix, let me also execute the program for diagonalization. What was that program for diagonalization? So, these are all the files in my matrices directory. The program for diagonalization was eiglar.f, that was the program for diagonalizing matrices. So, I shall use that program to illustrate how you can get a diagonal matrix. Okay. So, what I shall do now, I shall compile that. How do I compile? G. So, before I compile, let us just see what that file is. eiglar.f. I am editing that file. Okay. So, again there is nothing. So, it is eiglarge.f. Remember what I did? I tried to edit it as eiglar.g. So, there is no file called eiglarge.g. So, it gave me an error. So, I shall edit now Vi eiglar.f. Okay. So, this is my file. Again, since my view and your view is slightly different. Okay. So, this is my program large eigenvalue. So, it calculates iteratively the largest eigenvalue. So, I define exactly the same dimensions as the old case. I read from input 1 dot dat. So, read all the values of aij, and I will now first set up an initial eigenvector. My initial eigenvector is 1 0 0 0 0 and y0 is 0. So, this setting my initial eigenvector, okay, 1 0 0 0 and y is another 0. So, what I do in this program, I keep on multiplying with matrix A that eigenvector x many times, so that when I multiply by the largest eigenvalue, only the first eigenvalue will remain. Okay. So, now I will execute that. So, I am going to compile this program. Okay. Again G Fortran eiglar.f. Okay. So, when I did that G Fortran eiglarge.f, it gave me no error message, that means the program has executed properly. Now, I shall execute that. How do I execute? ./a.out. Okay. So, when I execute, these are all the results of my execution. So, let us see how it has executed. So, when I typed ./a.out, it first wrote my original matrix. Okay. And this first vector was 1. So, the first column is it tells me how many iterations I am doing in this program. So, first time the eigenvalue was 1 x, the x column had 1 and all the rest was 0. Okay. Second time I got my eigenvalue as 119.000 and this was my eigenvector. When I iterated again, that 119 became 119.04050231, 1, okay. 10 minus 2, 1.48 times 10 minus 3, 1.69 10 minus 3. When I iterate again, the next one is 119.05 and this is my eigenvalue, eigenvector is 1, 2.53 into minus 2, 1.56 into minus 3 and I iterate again. You see 6th iteration, it has not done the 7th iteration because the parameter I gave 10 minus 5 was the error I mentioned. So, if my new eigenvector, this is my new eigenvector, it does not change from the old one by more than one part in 10 minus 5, it will stop the calculation. First value, first column was 1, second value is 2.53625, the next line is 2.53643. Okay. So, it is changing by much less than the 4th digit. So, it converges at this point. So, this is my eigenvector. So, to now make sure that this is really the eigenvector, what was my equation? A x equal to lambda x. Okay. So, what I am typing here? I am typing A x and lambda x values. What is A x? I take matrix A, multiply on the vector x, that will be one way. The other way is I just take lambda and multiply that x. So, this is my x. In one case I have multiplied lambda into that eigenvalue and in the other case I have taken A into that eigenvalue. So, this is top line is A x, bottom line is lambda x, this is a 4 by 4 case. You will see that both A x and lambda x are identical to the 5th digit. You see that 109.05072, 109.05072. This is exactly the same. In this case, it only differs 01968, 01967. It only differs in the 5th digit. Okay. So, this means that I have a converged value. So, now what we have seen? We have seen that you have a matrix inversion program as well as a matrix diagonalization program which just gets the largest eigenvalue. When we operated both these, we got the correct inverse as well as the largest eigenvalues. I would urge you to practice this in great detail and any questions you have, you can send it to us, we will reply to you. And you have to practice all these programming because when you actually program, there will be many errors in your program. So, it is only when you master the art of correcting the errors, you progress in programming. So, this concludes our session on matrices. Next time, we will start with fitting a curve to a given particular data point. That is called curve fitting and that curve fitting requires matrix inversion. Therefore, we did the matrix inversion first and then curve fitting. So, next lecture we will do curve fitting, then we will do a little bit of integration, differential equations, random numbers, okay. Then we will go to molecular dynamics after that. So, I will conclude my lecture here. Thank you.